So we're actually going to go ahead and sort of back up and do the notes that we didn't do since we're so shy a class, so that we get to talk about them a little bit. And I wanted to go through your what do you know with you, since we finally did one for physics. I wanted to talk about it. So this chapter is all about work and energy, and the really awesome news is that you guys have lots of knowledge already about work, and a little bit less maybe about energy. So tell me everything you know about work in the science sense. Something does something, which is fantastic. You use forces to do work, and that's true. Work's the amount of force needed for an object to be moved. A few people remembered that work equals force times distance. It moves something. It creates motion. Here somebody has got two things sort of conflated, and the second one is better than the first. Work is the ability to do anything that requires energy. Energy is the ability to do work. We'll go with that. We'll strike that. Let's look at some more response. Okay, so somebody says it's the idea of doing one thing to cause something else to happen or get accomplished. Yeah, in a very real sense. Work, force applied to an object to move it. Force has to be applied to an object to move it. Work is the amount of force it takes something to exert on something else to cause it to move. Again, we have a little bit of fuzziness in our language, but that's okay.
I think that one was mine.
You think it's a little circular, but that's okay. We're going to clarify this. So work is the amount of force it takes to exert on something else to cause it to move. So let's get the third. Okay, work is doing something or applying a force to something, maybe?
That was me.
Some uncertainty. It takes energy to work. It requires that the object is displaced. Very good. Energy is the amount of work you can do. Good. Work is the displacement times the force times the angle. If the object's displacement is 0, its work is 0. Angle of work done cannot be 90 degrees. Okay, a lot of information. So let's look at the next one, which is all about energy. Everything you know about energy, it gives an object power to do work. It could be potential or kinetic. Energy is the ability to do work. The basic forms are kinetic and potential. It's never lost, only transferred. Energy is the ability to do work. I really like that because that's true. That's like a textbook definition. Okay, you use energy to work. Yes, energy necessary in work can be gained or lost. Well, not really. When an object has the potential to move or is in motion, it has energy. That is true. The amount of work force required to move some amount of mass over time. They have the idea of time in there, and time does come in with energy. It can be transformed, not destroyed. Different types cannot be created or destroyed. I don't know anything. Okay. Energy is the amount of work that you can do. Heat is a product. There are two kinds, potential and kinetic. Okay. Good. Let's look at our last question. Kinetic energy is moving. Potential energy is non-moving. There are different types. Potential is stored. Kinetic is motion. Potential is stored. Kinetic is motion. There might be different forms. I don't know. Potential is when you have the potential to move. Kinetic's when you're already moving. Potential is stored. Kinetic is motion. You guys know that. Okay. Potential is the energy buildup before it's in motion. It has the potential to move. Kinetic is when it's moving. Yes, there are different forms. Potential, stored. A spring. Ooh, the first mention of springs that is coiled back. Kinetic is released. A roller coaster traveling down a hill. Potential is the energy contained in an object before it moves. Kinetic is energy an object has while it moves. Potential is stored. Kinetic is moving, maybe. Okay, potential is energy that has not happened, be will. I think they meant but will. Like a roller coaster that crests a hill. Kinetic energy is happening like a roller coaster going down a hill. Kinetic is when something moves. Potential, not yet. Types of potential energy are magnetic, electrical, weak nuclear, strong nuclear. Those are actually the 4 universal forces. So those are a different thing. So good to clarify that. Magnetic, electrical, weak nuclear, strong nuclear. Those are actually the 4 universal. Those are the 4 forces known in the universe. So really important stuff, but not the same as energy. They can all create, however, potential energy. So any of those is capable of creating potential energy if you have a difference. Well, that's more complicated than we're going to get into. Potential energy, maybe going to move. Kinetic energy, straight rolling, or whatever form of motion you prefer. Yeah, I know, spelling, schmelling. Kinetic is when it's already moving, like down a hill. Potential is like at the top of a hill. Okay, So here's the thing. You guys know a lot already about work and about energy. Everything we're going to do is going to build off what you already know. So first of all, let's just clarify. If something doesn't move, no work was done. So I can set you all up against a wall, pushing all day long. If it doesn't move, you didn't do any work. Did you exert force? Yes, you did. However, you did not do any work in the science sense of work. And work is just WFD. So if D is 0, work is 0. That you already knew. Here's the thing that, and I quibble a little bit with how your book does it, so we'll talk about that. Work is only, so you know that we can have forces that are applied at some angle where not all of the force is on one axis. We've been doing this since chapter 2. We've been doing vectors for a long time. Work is only done when some component of the force is on the same plane as the displacement. So if we have force, if we have motion on the x-axis, the force on the x-axis is the only part that's doing the work. If we have motion on the y-axis, the force on the y-axis is the only part doing its work. Because work is only done by the components that are on the same axis, that are parallel to the motion. And remember, work can be positive or negative, just like forces, and work can slow you down or speed you up. Your rotors do work, your brake pads do work on your rotors when you brake your car. Not when you break your car, but when you apply the brakes and change your velocity. Okay. Okay. When the applied force is not in the same direction as the motion, we have to break the applied force down into its components. And the way the book handles this is to say that, oh, work is equal to FD cosine theta. I struggle with saying that it's always going to be cosine. I have not yet, this is my science thing. I haven't yet seen a case where it doesn't end up being cosine, but I can't say it's universally cosine. I would say look at the image. Look at where the force is being applied and where the motion is happening. It seems to always be cosine, but I just keep thinking that there has to be some other... and actually, you know what? It could... Okay, here it is. It would depend on how you're describing the force. You know, so just as we have described forces based on angles, you know, above or below the horizon. Oh, well, it's 20 east of north or 70 north of east. Well, same thing, depending on which angle you're describing for the force, it could be sine or cosine. Though most often the way that the angles are described, especially by your book, means that it ends up being cosine. And D is the same as delta x. We'll take 4 and come back. We very often commonly use D in place of delta x when we're doing work stuff. So it's the same thing, distance or displacement. And we can look at, of course, delta x, delta y, whatever. Same thing. You all did the practice problem. You all did the sample problems. Aren't those delightful? They're really darn easy. You know, it's 3-part algebra. Obviously, it's going to get a little bit more complicated, but yeah. But we're not doing the hardest parts in this chapter. What we do in this chapter is certainly relatively easy compared to chapter 4. Because chapter 4 really is about the hardest stuff we do. So, okay, so kinetic energy. Now we get to talk about KE. And you guys all know that it's energy in motion. And energy is the ability to do work. So energy is having the ability to apply a force and move an object.
Wait, that says A, B.
Okay, we did skip a slide, and it's one of my favorite bad jokes. Network. ABC, NBC, CBS, CNN, Fox, you take your pick, they're all networks. So when you have a bunch, and this is pretty second nature to you guys, this is like a 4A concept. When you've got a bunch of different forces acting on an object, you have to find the net force before you can find the work. Because the net force is what's going to accelerate it, meaning it's what's going to move it, So really that F is F net. And from there, once you can find F net, you can find anything else you want. So now we'll talk a little bit about kinetic energy. So energy is the ability to do work, and work means you're applying a force to something and moving it. So kinetic energy means something moving is able to apply a force and move something. If you roll a bowling ball down a bowling alley, when it strikes the pins, it moves them. It does work on the pins. It has kinetic energy. If the ball is just sitting there in the lane, it's got no energy whatsoever. Just sitting. Okay. So you know that some object, such as a bowling ball, that has some mass, that is moving on a plane when a force is applied to it, and it's got an acceleration. This is all true. So we could say that the force on the object equals its mass times its acceleration. Well, we can also say that the work being done on or by the object is equal to the force times the distance that it moves. Okay? I recommend that you actually step through this and do the derivations step by step. For most people, it's helpful. Okay, so we can suddenly set two things equal. We can take this mass times acceleration and stick it in there for force, so we have work is equal to mass, acceleration, delta x. Or work equals mad max. Mad max, yeah. It doesn't really work that well. Okay. If you go all the way back to your four golden equations, we have this. Vf squared equals Vi squared plus 2a delta x. Let's solve that for acceleration. Well, we'll solve it for ax actually. So Vf squared minus Vi squared divided by 2 equals a delta x. Hey, looky there. Isn't that handy? Okay, so now we can sub in and we get work equals mass times the quantity Vf squared minus Vi squared over 2. This isn't so bad, is it? Okay. So now we can, and I'm going to shrink a few things. Okay, so now what we can do is we can distribute everything. So distribute the m, distribute the 2. We get W equals m Vf squared, well, let me put a 1/2 in there. 1/2 Vf squared minus 1/2 m Vi squared. Okay, that wasn't so bad. You will end up wanting to do that, yes. Does anything about this equation look familiar to you? Are you suspecting that maybe it should, based on the fact that I'm asking you that? We'll give it some little radiance lines here. I would recommend it. So work is equal to 1/2 mass final velocity squared minus 1/2 mass initial velocity squared. Nothing is ringing a bell. Interesting. Interesting. This is so what? Suspicious. Yes, you should be suspicious. Okay, so remember that energy was the ability to do work, and 1/2 mv squared describes the kinetic energy of an object. Ke equals 1/2 mv squared at any given moment. So at any moment we can look at some object, take its mass times its velocity squared, divide by 2, and we have its kinetic energy. Now, since I have screenshotted these and I can't pop it up like I used to with the PowerPoint, just cover up that bottom line for yourself. Which is more critical? Kinetic energy is dependent on both mass and velocity. Which is more critical?
Velocity.
Velocity! Because it's squared.
It's squared.
There was a fantastic Nova special years ago, and I need to get like a 5-minute clip of it that I can interject here, because I don't want to have you watch the whole hour of it for the 5 minutes. That's really vital. Which was the space shuttle that burned up on re-entry in 2003, spring of 2003? Columbia. I get them confused because I was a kid when Challenger blew up, so I always mix them up. You know, Columbia had damage to the heat-resistant tiles, and so on entry, hot air was able to get under those tiles and then tear it apart, and then it tore the vessel apart. What they figured out did the damage to the tiles. Do you know what it was? It was a chunk of styrofoam. It was a chunk of styrofoam. So you know that like pink insulating foam that they have on houses? Have you ever tried to beat somebody with a piece of that?
No.
It's pretty light. I mean, go try to like pelt somebody with styrofoam peanuts. Woo, I'm so scared. You know.
Mom told me not to touch the Yeah, that's what I was thinking.
No, that's the fiberglass. We're talking about, this is styrofoam insulation. This is pink styrofoam insulation. It looks like pink styrofoam.
It looks
That's,
like it like started out as like.
so what they discovered is, so here's what happened. When the space shuttle took off, I'm going to draw a really terrible space shuttle. Okay, when the space shuttle took off, there was video of a piece of insulating foam, because there's insulating foam around parts of the fuel tanks, coming off the shuttle and hitting a wing at takeoff, during the takeoff process. Engineers were aware of this. And they said, it's just a piece of styrofoam. It's just a piece of styrofoam. Couldn't have done any harm. It's styrofoam. It's you know, incredibly light material. In the post-analysis, and the part on the Nova special that I found really, I mean, both chilling and fantastic, is another engineer who was not on that team saying, basic high school physics will tell you KE equals 1/2 mv squared. It's not the mass that will get you, it's the velocity. That piece of styrofoam was moving at, and he quotes whatever rate of speed. It was moving so fast, it had so much energy, it was able to do significant damage to the tiles, which, of course, they figured out in retrospect, unfortunately. Yes, everyone. So remember we had this. Well, what we're looking at here, since we now know that KE equals 1/2 mv squared, this is final KE. This is initial KE. Final velocity, initial velocity.
Wait, where does that F come
This, I mean, that F,
from? Yo, wait.
that's just final velocity. So in an object that is changing its velocity, the work is equal to the change in its kinetic energy. So if you think about that bowling ball moving down the lane, it has a specific amount of kinetic energy. If it was moving down an infinitely long lane, will it eventually roll to a stop? Yes. Friction is doing work on it. The floor is doing work on it through the force of friction. The floor is exerting a force on it through friction. Whatever its initial velocity is, squared times its mass divided by 2, its initial kinetic energy. At the point when it stops and its velocity is now 0 and it's got its final kinetic energy, the amount of work that was done on it by the floor can be calculated this way. We're going to do, it'll make more sense once we do the problems. So you can speed an object up by exerting a force on it. You can give something a shove and speed it up. And then, you know, its initial velocity will be lower than its final velocity, and you can still figure out the work that was done on it. Because remember, work can be positive or negative. Work can slow you down, work can speed you up. all that. All those things apply. So now, problems. Oh, geez, who spell checks this stuff? The net work, which we said was equal to F net D, or delta X, cosine theta. Well, the net work is also equal to the change in kinetic energy. Okay. So now we get to do some problems. Okay, page 173, the 5B problems we have. Hey, it's a bowling ball. I didn't. Actually, I forgot that there was a bowling ball here. And this bowling ball is moving at 3.00 meters per second. Okay, so these are pretty easy. This is just a KE problem. So we have a 7-kilogram bowling ball. This is probably a child's ball. It's like a 4.5-pound bowling. Oh no, that's a heavy ball. Actually, that's like a 12-pounder. Okay. What we want to know is what's its kinetic energy. So we have a velocity, we have a mass. KE equals 1/2 mv squared. We're simply looking for kinetic energy. So KE equals 1/2 of 7.00 kilograms times 3.00 meters per second squared. Do your math. Okay, so what do you get for kinetic energy? 31.5 joules, just like the book says. Okay, and joules are the unit of both work and energy, and a joule is a kilogram meter squared second squared, if you want to do the dimensional analysis. So 1 joule equals 1 kilogram meter squared over second squared. Set that aside. Okay. So we've got the KE for the bowling ball. Now the big question they're asking is if we also have a ping pong ball on the same bowling alley. In order to have the same amount of kinetic energy, how fast would the ping pong ball have to be moving? So to do this, we're going to obviously do a little bit of rearrangement. So we want to know how fast it has to be moving. So we're going to rearrange 2KE divided by M square root equals V.
Wait, is that grams?
It is grams, so we also have to do a conversion. Yes. So 10 to the third grams equals 1 kilogram. 2.45 times 10 to the third. So let's plug everything in. Whoops. That's to the negative third. I screwed up. Okay, so you've now got a problem. Plug it in. Okay, what you got for a raw answer? Three, 5, 6, 7, yeah, 451 meters per second. So the ping pong ball to have the same kinetic energy as the bowling ball would have to be moving at 160 meters per second. That's pretty crazy fast. Okay, strap it to a rocket. That'll work. That'll work. So, 1.60 times 10 to the second meters per second is the best way to get the sig figs on that. Your assignment for 5B is page 174, numbers 1 through 5. Okay, so no, it's not on the notes. 174, 1 through 5, and I just wrote it on the screen too. Okay, so that's it. I'll give you time to work, and
For 5C, which ones do we have to do?
all of them in the book. Yeah. 1.60, it'd be, if we go back to the original, 3 sig figs. Pardon? Meters per second, because it's just velocity. Okay, that's it.